Is that better? Is it working now? Hopefully it should be working. You should be able to hear us. Just waiting for somebody to save. See if you can hear us now. Yep, excellent. Right. I thought we nearly had a disaster already at the start. Excellent. Right, okay. So what we're going to do, has everybody got the questions downloaded? And it doesn't matter if you haven't done them. It doesn't matter. It just gives you a little bit of. I like to release them earlier, so you've got a bit of prep, so you can have a look at them, and then we can go through them. But if you haven't, then go and have a look in the link in the description box. Go and have a look there, and then see if you can get a hold of them. And I'll go through them on the slides here. And I've actually decided, instead of using the whiteboard on the tablet, because it seems to just not work at all, the computer just can't seem to handle it, I've actually now got a proper whiteboard, so I'm going to use that instead. So hopefully that's good. So I'll just give you a minute or so if you haven't got the questions already. So that should be them there. If you haven't got them already, then get a hold of them, get them open, and see if you can do it. We'll make a start in about 30 seconds. We'll make a quick start. I'm aiming to get this all done within the hour. That's the hope. I know last time it ran over a bit because the computer decided to crash, so we're going to do it hopefully within the hour. So, okay. Right, okay, so what we're going to do, we're going to start with the first question. People who've done them already, did you find them quite difficult? I know this was something that a lot of people wanted help with. A lot of people wanted help with this, so I thought we'd just go through some of the ones which are quite generic. So it'll cover all main exam boards. I tried to pick mechanisms that you could do, and I picked the AS ones as well. So there's no, yes, it is for all exam boards. Somebody's just put on there, but it is for all for exam boards. But I've done a little chart where we've literally ticked off for all the different exam boards, as you can see on there. That's gone a little bit blurry. Anyway, right, okay. So let's make a start then, shall we? So we'll start with. Let's hope this works. Everything's going to be on here or behind me, like I say. So hopefully this should work quite nicely. Right, so the first question, what I decided to do is to do some radical ones. I know it's not a traditional mechanism with curly arrows and everything, but what we're going to do is look at some radical mechanisms, then we're going to look at some traditional curly arrow mechanisms, and I've used them, integrated them as exam papers, exam questions as well. Right, so the first one is methylbenzene is converted into chloromethylbenzene in a free radical substitution reaction, okay? So I know there's a bit of benzene in here, but it doesn't really matter. The benzene bit's not relevant here. Okay. Write an equation for the initiation step. So remember, if it's initiation, it means that you're forming a radical. You've got to form a radical from something that isn't a radical already. Okay. So the initiation step with this one, and this is suitable for all exam boards, all major exam boards. So if whatever you're doing, you'll definitely need to know this one. Okay. So the first thing you need to do is have your non-radical. You're going to add UV light to it, and then you're going to turn it into a radical. So the equation or the reaction we're looking for is we need a halogen radical. Okay. The reason why we need a radical is because alkanes, when we're adding anything to an alkane, they're notoriously unreactive, and so you need an incredibly reactive species to actually get this to work. So the first step is this. So it should be chlorine forming Cl2 or 2Cl dot, should I say, or you can have the half molar, that's fine, okay, to form one chlorine dot. So the initiation step in any mechanism, radical mechanism, is you start with a non-radical and you form a radical, okay? So remember, a radical must have that dot on the end, as you can see there, okay? So very, very important, it must have the dot, because that shows you've got an unpaired electron, okay? Right, okay, so I haven't got any questions coming through for that, so I'm going to move on to the next question then, if that's okay. Right, so the next part of this, with any form of radical reaction, remember you have initiation, and then you have your propagation steps, and you have termination. Okay, so the propagation is probably the most difficult bit, I would imagine. So we've formed our radical, So now what we have to do is write equations for the 2 propagation steps, and we've got 2 marks addressed for this one. Somebody's put, do you write UV light? Yes, you need to put UV. You can write that above the arrow for the previous one, so that's fine, yeah. Right, so 2 propagation steps. So you've formed a radical, okay, so your first propagation step must always be the radical reacting with your alkyl group. In this case, it's going to be your methyl benzene group, okay. So that's the first step. So there it is, okay, so radical plus your methyl benzene, and this is going to form, it's a bit like past the parcel, except this is past the radical. So what happens is the radical is then switched from the chlorine, okay, so the chlorine takes hydrogen from the methyl benzene, and it forms, the radical now jumps onto this intermediate here, this benzyl compound here, and then you form HCl. So with the propagation, you always have radical plus non-radical will give radical plus non-radical. You always form that same type of step, okay? So that's the first step. Everybody following so far? So you get 1 mark if you've put that, so that's good. And then the second step is it's always, and when you're doing propagation reactions, you always put your radical that you produced in the first step is always a reactant in the second step, okay? So here we go, we've got a radical here, we bring that radical down to be a reactant there, and it will react with the original molecule that you had initially, which was chlorine, okay? So that reacts with that, and then what happens, it's past the radical again, so your radical then moves from the benzyl compound here, okay, to the Cl dot. So you form that Cl dot back again, and hey presto, you formed your, you've added your halogen onto this compound here. Okay. So the reason why, like I say, I emphasize this, the reason why radicals are used for this reaction is because alkanes are notoriously stable. They're really they're not reactive whatsoever. So you need something with a bit of punch, like a radical, to actually add onto the compound. Okay. So if you've got them, you get 2 marks. You get 1 mark each for each of them. Okay. Right, any questions on that so far? If you have, just keep putting them in chat. I don't think anybody's put any questions on that, so that's fine. So it must be them 2. Remember them rules there. Okay, so you form your radical in the first step. So you use radical, non-radical, and it forms, you pass the parcel, and the radical is then reformed the chloride radical. OCR A mark schemes don't need the radicals. Yeah, so you do OCR. I've checked all this. OCR you do need radical. You do need to know these radical reactions. Especially in another example might be the depletion of ozone. So you are expected to be able to write these equations. It's not like a traditional mechanism where you have curly arrows. This is just like written in lines instead. Okay. Right. Okay. So let's go on to the next one. So give the formula of another possible organic product of the reaction. Okay, so remember we've got initiation where the radical's formed, propagation where you have this pass the radical around, and then the last step is always a termination reaction. So termination is always where you have 2 radicals that collide together and then you form a non-radical molecule. Okay, so termination must always be 2 radicals that are formed. Now you can have a plethora of different radicals that are around here. You've seen you had a Cl dot radical, you had your benzyl compound, which is a radical as well, and you've got loads of different types. So the termination step here could be any one of these. Okay, so you can either have your CH5CHCl2, or you can have C6H5CHCl2, or it can, because these things can continue to react, you can get multiple substitutions. So you can get 2 chlorines attached to it, you can get 3 chlorines attached to it, so these can continue to react. And then, or what you can have is 2 benzyl compounds, 2 benzyl radicals combining together, so your methyl benzyl radicals that combine together to form effectively 2 benzene rings that are joined together. Okay, so you can have various different termination reactions. So if you've got any one of them, give yourself a mark. Okay. Right, any questions on that so far? I don't think any's come through so far, so that's good. So I think the key thing with radicals is just making sure that all your atoms add up. You're not missing any atoms, and sometimes in the exam they can actually give you, like here, we could give any type of answer because it wasn't specifically asking for anything. But they may ask specifically for a compound that's produced, a specific compound that's produced using termination reactions. Okay. Right. Okay, can you explain that again, please, about the other possibility? Okay, so yeah, so what you've got, when I say the other possibility, these are basically, you see these reactions here, you've got various different types of termination reactions. For a termination, all you need is two radical species actually forming again, okay? So the reason why we can get dichloro and trichloro, as you see there, the reason why, assume the right termination, no, yeah, so this is the termination step, but the reason why you get multiple, you get dichloro or trichloro, is because the product that you produced in that previous step, that can then go on to react with the Cl dot as well. Okay, so you remember we formed our monochloro compound, so that was one of our products. That is not immune to attack from a radical. If you've got another Cl dot radical flying around, they're going to react and you're going to form a dichloro. And that dichloro compound can then react again with more Cl dot to form a trichloro. So it can keep on reacting. It's like we call it a chain reaction. It just keeps going. These radicals are incredibly reactive and they're quite destructive. They cause a lot of problems. Okay, yeah. So they're your different products, but again, the exam board might give you specific examples as well. Right, so that's what exam board is this? This can be applied to any exam board. I've done a check on the major UK-based exam boards, AQA, Edexcel, and OCR. So you are expected to write radical reactions mechanisms like this. So initiation, propagation, termination. So I've tried to keep these as generic as I possibly can. Okay, some exam boards, for example, AQA has loads and loads of mechanisms, whereas OCR probably has the least. Edexcel somewhere in the middle. So I've tried to get some common ground on all of these. So just to make sure it appeals to most people. Okay. But when do we know that two radicals will collide and cause termination? So this is just, if you have two radicals, wherever two radicals collide into each other, remember you've got loads of different species floating around. Wherever you have two radicals reacting with each other, they will form a non-radical. They effectively cancel each other out, and you always form a non-radical molecule. Okay? Do the dots on the radicals go before or after? I normally write them after. It's just the way that I've always done them. I don't suppose it would make any difference if it was before, but that dot must be there, otherwise it would be mistaken for a chlorine atom. Okay, so the dot just represents that you've got an unpaired electron, and that makes them really, really reactive. Okay. Okay, which two radicals form to form the last product? So the last product there is two methyl benzene radicals. They join together. So remember we formed methyl benzene in the previous step. So if we have them two joining together, we form this effectively double methyl benzene structure. Okay. Why is the radical different to an ion? Yeah. So a radical, an ion is formed when you lose or gain electrons. A radical, for example, a chlorine atom is effectively a radical. So you just have you have an electron that's not paired up that would normally be paired up. So they're very, very reactive. If you imagine chlorine with it has 7 electrons in its outer shell, 6 of them are paired up and 1 isn't. That's really, really reactive, and it's why chlorine goes around as a pair, because it's far more stable than just floating around as an atom on its own. Yep. Okay, right. So let's have a look. Let's go on to the next question. Just to try and keep pace, we're 15 minutes in. So that's one question out the way. So it's we're probably on time to finish in an hour, like I say. Okay, so the second question, bromoethane. Okay, so that reacts with sodium hydroxide in an elimination reaction to form ethene. Okay, outline a mechanism for this elimination reaction. Okay, so what we've got to do is we're going to draw down a mechanism for this reaction. Now this one is, if you do an AQA, I believe you need to know 2 types of reactions. You need to know, let me just check, AQA or Edexcel, you need to know if it's dissolved in water, it follows a different mechanism to if it's dissolved in a base, for example. So in alcohol, sorry. So this one is an elimination reaction. So OCR, you do need to know this as well. So this is a specific example. So let's have a look. So we've got outline a mechanism for this elimination reaction. So there's a lot of steps here. Okay, so I'm going to spin round and use my whiteboard, and hopefully this should work. Let me just move some of this out of the way. Okay, right. So let me know if you can. Let me just squeeze that back a bit. Can everybody see the board? I'm going to make this bigger. Please bear with me 2 moments. Okay, right. can everybody see the board now? Is that clearer? If you just give me the thumbs up just to say that you can see it. Yep, fantastic. Right. Okay, so what we're going to do is we're going to draw a mechanism for this. It's 3 marks. Okay, now there's particular skills that you need to know. Okay, wow, I know. Is that because I've actually managed to get the screen to work? Right, so the first one, we've got our halogen. So we're going to write it here. So we've got, let's write our molecule here. So this is our haloalkane, should I say. So we've got 2 hydrogens and a bromine. Okay? Yeah, much better. Okay, so can you see that? Is that alright? Should be able to. If somebody let us know in the chat just to make sure you can actually see that. Perfect. Right, okay. So, we're going to react this with an OH minus. Okay? So, we've got an OH minus. Now we have a lone pair of electrons on the oxygen. Okay, so we have a lone pair that's on here. Okay, so what we're going to do, this is an elimination reaction. So this is going to attack hydrogen. So hydroxide here is adding as a base. It's not acting as a nucleophile. Okay, so this is going to attack a hydrogen. It's going to attack a proton here. So you must show your lone pair of electrons. That's really important. You must show them on the OH minus. Okay, and then that must attack. The electrons here, the arrow must go to that hydrogen there. Now it can't go on the hydrogen that's bonded to the carbon directly to the halogen we want to kick off. It must be bonded to an adjacent hydrogen to the carbon with the halogen on there. Okay, very, very important. So that's this is a 3 mark mechanism. Okay, so you get 1 mark for that arrow. Okay, then we need, this is going to break off. So this is forming a bond. Wherever we draw an arrow in mechanisms, this means that the hydrogen is forming a bond with the OH minus. Okay, why is it not attacking the carbon atom? It's not a nucleophile. Yeah. So there's 2 types of mechanisms for I believe it's AQA and EdXL. If this is dissolved in water, then it acts as a nucleophile. If it's dissolved in alcohol, it acts as a base and it attacks that hydrogen. And also it says in here as well, it's an elimination reaction. So because it's an elimination reaction, then we must draw it using this mechanism here. There's 2 types for this one. Halogenoalkane with hydroxide, depending on the solvent, will depend on what type of mechanism you're actually going to draw. Okay, so that's the first step. Then what we do is we draw our arrow from, now this is very, very important, it must go from the carbon-hydrogen bond, the arrow must go from that bond there to the bond in between the 2 carbons. Okay, so this is not electrophilic, this is a base, because it's accepting a proton. This is OH here, and this reaction is acting as a base, it's not a nucleophile. Okay, if it was a nucleophile, it would go for the delta positive carbon in the middle there. Okay, so electrons, the arrows always show the direction of electron transfer. So this is going from the bond into the double bit there. Okay, so that's forming the double bond, and because it's a double bond that's being formed here, this carbon now effectively has 1, 2, 3, 4, 5 bonds. So one of the bonds has got to break. So the one that's going to break is this one. So we're going to, the electrons from this is going to go onto that bromine there, and that's going to break that off. Okay, so there's 3 different marks there, and obviously we're going to write down our product. So our product is ethene, so C, double bond C, hydrogen, 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 and hydrogen. Okay, so you should have your alkene, and then we have this OH minus reacted with a hydrogen, so we'll have water. Okay, so we'll have water, and we'll also have, because this was reacting with sodium hydroxide, so because it's sodium hydroxide, then the sodium that's floating around, there is sodium around here, will effectively react with this bromide that's being kicked off. So we'll also form sodium bromide as well. But your marks come for all these arrows here. That's what we need to do. Okay. OCR A only mentions the C acting as a nucleophile. So as far as I'm concerned, when I checked it, let's have a look. So we're forming an alkene. Yeah, no, you do need to know it for OCR. It is in the specification. That's as far as I'm aware. That's sort of when I looked at it. So it's just to try and keep it generic. I think if you're doing Edexcel, you don't need to know the actual mechanism for this. So yeah, so that's your reaction. Can everybody see that on there? Do you need to put the delta negative and positive? Normally you do if you're talking about nucleophilic reactions here, but because this is acting as a base, you don't need to put them on. If you put them on, you're not going to lose marks. So it's probably a good habit to get into, isn't it? So you know exactly what's going on. Okay. Right. Okay. So just so you can see that, so that's good. Right. Do you need to put the in a displayed form here? Do you still need to show the charge? You do need to show the charge here, yes. You need to show your charge. You need to show your lone pair of electrons on the oxygen. That's really, really important. Where did the sodium come from? If you look in the question, it says sodium hydroxide. Okay, so the sodium is there. It just doesn't get involved with the intricacies of the reaction. It only gets involved when the halogen's kicked off, then the sodium's there. Because remember, this bit here is from sodium hydroxide. That's where that's from. Okay, but the sodium is a spectator ion. It doesn't actually get involved with the full reaction. Okay, yeah. You don't really need to. Okay, yeah, that's fine. Right, so let's move on to the next question. Okay, so I'm gonna shrink this down. Okay, there we are. There we are. I'm getting better at this technology. Right. Okay. So let's have a look at the next question. Okay. So part 2. Suggest one reason why this method for making ethene is not used in industry. Okay. So we've actually gone through. Yeah, so we've gone through these different types of reactions. Obviously, we've seen that mechanism there, but in industry, why don't we use this method to do it? It's mainly a practical use, really. But there's a few different types, few different reasons here. So your haloalkane is made from ethane, which is quite an expensive because it comes from crude oil. Or your haloalkane is not readily available, or it's expensive. That's normally a reason. Or it's the yield is low, it's poor, or it's too slow. Anything like that. Yep, lower yield is fine. Yep, lower yield is absolutely fine. Okay. So anything like that should be fine. Okay. So pretty straightforward. And normally when they ask questions like this, why is it not used in industry? You think about cost, you think about safety, you think about the practicalities of it in terms of the time it takes. Normally that's the type of answers they're looking for. Okay. Right. Okay. Everybody happy with that so far? Yeah. Okay. Yeah, so this, I must emphasize again, this reaction here is an elimination reaction, okay? So when it's elimination, the hydroxide acts as a base. It takes a proton or hydrogen from that molecule, forms the double bond, then kicks off the halogen. If it was a substitution reaction, okay, then your hydroxide would attack that delta positive carbon and then just kick off your halogen. Very, very important. That's a nucleophilic substitution reaction. This one is just elimination. So the hydroxide's acting as a base. There is. Don't worry. It's not. There is two mechanisms with a haloalkane and OH minus. There's two different types of mechanisms. The solvent that you dissolve it in plays a role in that. So, for example, in this one, this is obviously an elimination reaction. So the solvent we use here is an alcohol. Okay, but if you are doing AQA or Edexcel, you also need to know if it's dissolved in water, it undergoes nucleophilic substitution. Okay, if you're doing OCR, you'll need to know that mechanism. Okay, if you're doing AQA or Edexcel, you need to know that one as well. Okay, right. Okay, it's difficult, you see, because there's loads of each exam board decides to use mechanisms, some don't. You see, so right. Okay, so let's have a look at the next question. Okay, so I think we're on time. We're still on time, so about halfway through. Okay, so look at question 3. There we are. Okay, so question 3. So compound X, which is this compound here, can be formed from a haloalkane, okay, which is C3H7Br. We're going to name compound X. Okay, so see if you've got this right, but compound X should be 2-methyl propane nitrile. Okay, so the reason why it's a nitrile, the classic sign of a nitrile is that CN at the end there. So that's a classic sign of a nitrile there. Okay, and it's 2-methyl propane nitrile because we've got 1, 2, 3 carbons, and we've got a methyl group hanging off the second carbon there. Okay, so that's the formula there. You'll find the exam board will give you it because it's not easy to spot it here. What I find is easier, it's a bit of an exam technique one for you here, is you draw this out as a displayed formula. Okay, so draw it out. So get your molecule there, draw it all out with all your bonds, and then it's easier to name. But you'll find they will do this. They'll give you a formula like this, which is pretty horrible to try and work out the name of it. But what I would do is break that down into a displayed formula and then work it out from there. Okay, yeah. So somebody said, how do you know if a methyl is branched? What I would do, where you see brackets on there, that tells you that it's branched. Okay, so we've got CH3 is actually branched off from this molecule here. Anything that's in a bracket tells you it's branched from somewhere. So in this case, we've got 2 CH3s branching off from that CH there in the middle there. So that's what it's saying. So this telling us we've got 2 CH3s branching from this carbon that it's next to. Okay. Yep, people are saying it's the brackets. Fantastic. Okay. Like I say, easiest thing, draw that out, and that makes it a lot easier. Right. Okay. So let's have a look at the next question. Okay, so give the reagent and conditions necessary to form X from C3H7Br, and we've got 2 marks. Okay, so we've got to write down the reagents that are required for this, and then we've got to write down the conditions as well. Okay, how could you draw it? Do you want me to draw it for the previous question? I'll quickly draw it on here. Let me just go back. So you've got, whoops. Just so you can see. Okay, so you've got CH, C triple bond N, and then you have a CH3 group on the top there, and a CH3 group there. Okay, that's how you draw it. Obviously, you draw all your bonds there. That's. Don't get into that habit. If you ask for a displayed formula, always draw your bonds with your carbons. I'm just being a bit lazy here. Okay, but basically you get the idea. That's how it's formed. So you can see we've got 3 carbons in a row, so that's prop. Yeah, and you've got your methyl group hanging off your second carbon, which is there. All right. Can you zoom in? Yeah, sorry. Yeah. Let me just grab that. There we are. Okay, so can you see that? So you have your 3 carbons there and you have your methyl group on the top there, so you should be able to see it. Perfect. Okay? Right, brilliant. Okay, so let's come back onto this slide here. So let me just drag this screen, shrink me down there and squash me down into the corner. Right, okay. So if we just come back to this original question that we were looking at before. Okay. There we are. Okay, so give the reagent and conditions necessary to form X from C3H7Br. So we've got 2 marks there. Okay, so so the first thing, and you might have seen this reaction before. The nitrile reaction is specifically, let's have a look, specifically for AQA and OCR. But in OCR you would do this in year 2. So if you haven't done year 2 stuff, this might be a little bit strange. But you will need to know it eventually. So the reaction conditions here, to form that nitrile from your haloalkane is use potassium cyanide, and the conditions is it's dissolved in alcohol for this type of reaction. Okay, well done. Yep, KCN, ethanolic, and warm. Yep, so you need a little bit of heat. How do you draw CN in a skeletal formula? All you do is you have to write it actually as CN. You put C triple bond N. In the skeletal formula, yeah, so you must draw it like that. Okay, so these are the conditions that are required. So you need to use KCN and dissolved in alcohol. Does it have to be KCN? You can use either, yeah, KCN or HCN. HCN is really difficult to handle. It's a gas and it's horrendously toxic. Potassium cyanide is a solid. It's much easier to handle. So you'll find, but either will work. Either will work. It doesn't really matter. The only difference is with HCN is actually it's really acidic, so actually you have the acid there to allow this reaction to go. So yeah, so you can use either. Right, so, fine with that? Okay, so the next question, or the next part of this question was name and outline the mechanism for this reaction, showing clearly the structure of C3H7Br, and we need to name, we need the name of the mechanism, and we need to draw it out as well. Okay, so let's have a look. So let me just get my notes from this. Okay, so what I'm going to do, I'm going to swivel round to the whiteboard again. Okay, so I'm just going to make that a bit bigger. Okay, so you should be able to see that there. Okay, so let's go back to the whiteboard. If I can squash through. There we are. Okay, so I'm just going to rub all this off. It's a lot better on this, I think. At least it's not going to crash, but I hope it's not anyway. Right, so the mechanism, so I'll go through the mechanism first, and then once we've gone through the mechanism, then what we'll do is go through the name of it as well, because we have to name it. So we're going to draw out our molecule, okay, first. So it's C3H7Br, okay, so we have our carbon in the middle, we have CH3, we have a CH3 on this side, okay, and we have hydrogen, and we have our bromine on the end there. Okay? Can everybody see that so far? I should be able to. I think I'm just looking at the screen here because I can see myself in there. So, which isn't pleasant. Right, so we're going to look at your Cn. Okay, you have your lone pair of electrons, and you have your negative charge. Okay, on your molecule there. So this is the start bit, okay? So we're going to have a look. We've got a cyanide molecule here, okay? It's got a lone pair of electrons here, and it's got a negative charge, okay? This is where we can actually add. So let's write it in green. Tell me if you can't see this green. But this is no, that's probably going to be too pale, I think. Okay, so what I'm going to do, I'm going to draw that in red. Okay, so we've got a delta positive here and a delta negative there. Okay, so always, why do you draw your lone pairs like that? Don't know. You can draw it as dots, you can draw it as crosses. I think I got in the habit of drawing it as crosses because dots can also represent radicals. So, but you can draw it as a cross or you can draw it as a dot. It doesn't really matter. Okay. Right. So we've got the lone pair of electrons here. Okay, so this is coming from our molecule, and then we're going to draw our curly arrow. So remember, curly arrows always go from the lone pair to the atom that it's attacking. So in this case, this is a nucleophile. So this is going to attack that delta positive carbon in the middle. Okay, so substitution reaction. So it's got to be like that. Okay. Then this is effectively forming a bond with that carbon. So this bond is then going to break, and it's going to kick off that halogen there. Okay. And so then the product we should form is, let's have a look. So we should have CH3, C, CH3, C triple bond N, and then we have a hydrogen at the bottom. And then obviously we've just kicked off our bromide, so we have Br minus. Now if this is potassium cyanide, then the potassium would react with the bromine to form potassium bromide. Okay, so that's really important. Okay, so this one is a nucleophile. Okay, and it's substituting the bromine. So this nucleophile here is kicked off the bromide, and we've now got a nitrile, which is over here. Okay, so how do you know if it's substitution? By looking at it. If it's substitution, you know, because if you look at your product, if you look at your reactant here, okay, this did have a bromine on, but your product now has a CN, and there's no bromine on there. So because before there was a bromine and afterwards there isn't, then this is a substitution. This is a substitution reaction. Okay, so that's the key thing. If it's elimination, you always form a double bond when it's elimination. So that's how you know it's a. If it's an elimination reaction, you must get rid of atoms, and if you're going to get rid of atoms, you must have a double bond in there somewhere. Okay. Is there a lone pair on the bromine? No, well, there is, but it's not relevant in this, so we put the Br minus. Put a Br minus on there. Okay. All right. Okay. So that's your reaction. So the name of the mechanism. So this bit, by the way, gets you 3 marks. Okay. So you get 1 mark for drawing your arrow here, 1 mark here. Okay. And then you get 1 mark for actually drawing your product as well. Okay. Could you use an SN1 mechanism? Yes, you could. SN1 is only applicable to, I believe it's LXL, so don't worry if you panic and you do AQA or OCR. Yes, you could use an SN1 reaction as long as you're showing the mechanism, the actual arrows where the electrons are moving to. Okay. So this one is a substitution reaction. It's nucleophilic substitution. That's the name of the mechanism. So you get 1 mark for naming the mechanism as well. This is acting as a nucleophile because it's going for that delta positive carbon. Nucleophile means nucleus loving. Okay, so this is going for something that has a deficiency of electrons. So this one has a deficiency of electrons because you've got an electronegative element next to it that's pulling these electrons towards itself in this covalent bond. So this one's a little bit deficient in electrons. That means it's open for attack from something like this, which is a Cn minus. Okay. Right. Okay. Okay. So let's go for the next one. Make sure I'm not getting myself stuck. Right. Okay. So how are we doing for time? We're fine for time. Okay, that's good. Right. So I'm gonna. Whoops. I don't want it to do that. Okay. So let me just. There we are. Okay, so we make myself smaller, shrink myself down at the corner again. I'm getting used to this, I think. Right, so, okay, so there are your 4 marks. That's where you get your 4 marks from, okay? Right, so, let's go for the next question. Okay, so this is the last question. This is question 4, okay? So, if it's elimination, why is it attacking the carbon, not the hydrogen? Sorry, I didn't see that. If it's elimination, then you must remove atoms from the molecule. So if it's an elimination reaction, then you always form an alkene. So it's going to attack one of the hydrogens. You're going to remove one of the hydrogens from there, or another molecule. Okay. If it's a substitution reaction, you have the same number of molecules as what you did before. You just swap in one of the functional groups from the original molecule for another one, and so therefore that is a nucleophilic substitution. So you must have that there. Yeah. So if it's elimination, why is it attacking the carbon, not the hydrogen? This is not elimination, though. This reaction. This is a substitution reaction. So the answer was what was it? Nucleophilic substitution. Okay. So it was a nucleophile. Okay. Right. So this one. So draw down a mechanism showing the. Isn't it more likely to be SN2 the secondary? Yeah, you can write out your transition state. This is really just looking at the mechanism. So that if they ask you specifically to draw it down as SN1 or SN2 mechanisms, then that's fine. But this one they haven't, so it's just a general mechanism, so you don't need to worry too much about that. Okay. Right, so we're going to come back to the whiteboard for this one. So it says draw down a mechanism showing the reaction of HBr with but1ene, which is that molecule there, showing the formation of the major product only. Now this one is quite an interesting one because we've got an asymmetrical alkene. Okay, so in other words, the double bond is pushed to one side. So now what we have is we actually form 2 different products, a major product and a minor product. Now, if you have depending on the exam board, you'll use a particular phrase. I don't want to mention it yet because it's going to form part of the answer in the last bit. Okay, so I'm going to go through the mechanism now to see if you can, to make sure that you can do it, and then what I'll do, I'll mention that word that's quite important towards the end. Okay, so I'm going to rub this off. I'm going to make myself bigger again. Right, there we are. Okay. Right, so let's. Ooh, I really do need a bigger room. Right, okay, let me just. There we are, that's better. Right, so we're going to rub all this out. Okay, right. So another mechanism. So this one is where we're going to. This is an addition reaction. Okay, so we have an alkene, and we're going to add something to this alkene. Okay, so it's an addition reaction. So one of the key things you'll notice with these types of reactions is that double bond. It has loads of electrons in that double bond. So the electrons, remember curly arrows, and I think people get confused. I put this one in particular, not only because you get two different products, but also because I think people draw the arrows. A number of times I've seen people draw the arrows the wrong way around, and these is, well, for every pound that I had that, I'd be very rich. But you've got a double bond in there, and that double bond's got loads of electrons, so the arrow is really important with this. So let's have a look at the reaction here. Okay, so we've got, whoops. Okay, so let's draw a molecule out. So we've got CH2, I'm going to draw it out along here. So hydrogen, carbon, hydrogen, and we've got double bond, CH2, CH3. So what I'm going to do, I'm drawing it like this because it makes it a little bit easier to kind of show you what's happening with the double bond. So I'm making the double bond the centre of the attention here. Okay, so you can see this is our double bond here. Imagine that's just CH2, and then you've got CH, and then it continues here, CH2, CH3. So you see you've got your 4 carbons on that long chain there. Okay, hope that doesn't confuse anybody with that. So what we're going to do is we're going to react this with HBr. Okay, so hydrogen bromide. Okay, so watch out for these types of reactions here where you've got an asymmetrical alkene and you've got a hydrogen halide that's been added to it. So what we're going to do is going to draw delta positives, delta carbons on this. Okay, so we've got a delta positive here and we've got a delta negative there. Okay, so we have a polarity, we've got a polar molecule here. Okay, so what's going to happen is we're going to add to this double bond. Now, one of the mistakes that people make is they start drawing electrons coming from here to this double bond. It doesn't happen. All curly arrows show the direction of electron transfer. There's loads of electrons in this double bond because it's a double bond. There's loads of orbitals overlapping, forming this double bond. So because it's a double bond, the electrons are going to come from here and they're going to be attracted to something that's slightly positive, which in this case is going to be a hydrogen. Okay, so what's going to happen is the electrons from here, they go into that delta positive. Okay, very important. Then once it does that, this is effectively forming a bond with a hydrogen. So the electrons from this bond go into that bromine there. Make sure you're drawing your arrows precisely. It's coming from the double bond, not from an atom, from the double bond to that hydrogen. And this arrow is going from this bond to the bromine. You can't be sloppy with your arrows. You've got to make sure they're going from the right place to the right place. Okay, so that's that one. Then we're going to form an intermediate. Okay, so here it is. So we're going to draw an arrow here, and we're going to have CH3. The reason why it's CH3 is effectively we've added this hydrogen on this side, so we've got CH3 there. Okay, we've got a carbon here. We've got our CH2, CH3 up at the top there. Okay, we have a hydrogen there, and then we have a positive charge, which is there. Okay, so we form a carbocation intermediate. Okay, very, very important. So then what we have is we have a okay, I'll just use this. So this bromine, remember this bromine here wasn't actually being used, so the bromine is still floating around, which is here. Okay, so the Br minus. Now this, somebody asked, does bromine have a lone pair of electrons? It does. This is where it is important to include your lone pair of electrons. So your lone pair of electrons are here, so that's on the bromine, the bromide ion, should I say. Okay, this is now going to attack this. Okay, so the arrows always go from the electrons to the positive charge, which is there. Okay, always goes. Remember, for arrows, curly arrows, they must always go from somewhere where there's loads of electrons to somewhere where there's deficiency, always. So loads of electrons here, loads of electrons here, and it goes into there. Okay, and so then we form our product, and our product should be this. I'm just going to draw it down here. Okay, so we should have carbon, CH2, CH3, hydrogen, and then you have your bromine there. Okay, So that's really, really, really important. So you can see here, this is a, how many marks is this? This is for 3 marks. So we're looking for 1, 2, 3 marks. Okay, so there's an intermediate that's been formed. Okay, make sure you're being really specific with this, and obviously we're forming our product here. Okay? Okay, right. So I don't think there's any questions on that. There's nothing coming through. So, okay, so let's pull myself through. Okay, so let's make myself a little bit smaller. Fantastic. Okay, would we say each of the double bonds is broken? My teacher mentioned something about pi and sigma. Yeah, so you've got pi and sigma bonds are mainly to do with the orbitals. You don't really need to be too... What I want to try and do is, okay, it's relevant in another topic, but if we strip out some of that complexity and keep it straightforward and keep it simple. So when we're looking at this, you can see that we've got our double bond there, so that's really important. We're breaking that double bond, the electrons are coming from that into that hydrogen there. Okay, so the major product is this. Okay, so this is your major product that we've just drawn out there. Okay, so that is your major product that's been formed there. That's your major product. Okay, the hydrogen's obviously been added at the end. I'll come back into that in a moment, but this is the major product. I'll come back to this in the last question. Okay, so the whoops, let me just get back onto the right screen. Okay, so let's look at the next question. I'll come back into that in the last question because that's going to be quite relevant actually. Okay, so we're going to name the product for 1 mark. Okay, for this one. So the name of the product is going to be 2-bromobutane. Okay, so you've got the bromine on the second carbon of that butane molecule. Okay, so as long as you've got that, that's fine. Okay. Right, and then the last question. So we're keeping good time here. I've actually kept within the hour, which is the objective, so that's good. So why is the product named above the major product? Okay, so what I'm going to do, I'm going to come back to this board and explain what we're looking for. Okay, so let me just make this a bit. Whoops. I'm just moving the actual screen around, which is not what I want to do. Okay, right. So there we are. That's better. Okay. So I'm going to come back to this again. Okay. So this is that word, and we're going to tell you about this word, this key word that I said we're going to talk about here. Okay. So you can see, you might think, well, hang on, I've added this hydrogen here. I deliberately haven't mentioned it because of this last question here, but deliberately added the hydrogen to the end here. You might be thinking, well, why didn't you add it to this carbon here? Why didn't you add your hydrogen there? Okay. So what you get is there's kind of 2 products that are being made, and it depends. It's all about this step here. Okay, so here the hydrogen was added to the end carbon here, so you've got 3 hydrogens at the end. Okay, we could have had our hydrogen here and add it there and have our positive charge on the end carbon here, so we could add it there. Now this comes into, and it depends on what you're studying. With the AQA you won't need to know this, but if you do OCR or LXL, you would have heard of Markovnikov's rule. Okay, and basically, to strip it back simply, the hydrogen here will add to a carbon. That means the intermediate would have is either a secondary or a tertiary carbocation. So in this case, this carbocation is a secondary carbocation. Okay, so the hydrogen will add to this side here because this means we form a secondary carbocation. Your secondary carbocations are more stable because you have this group here, this methyl group here, and this ethyl group are pushing electrons into this carbon to try and stabilize it. Okay, your secondary carbocation is much more stable than if your carbocation was on the end here. Okay, your positive charge was on the end, then it means it would only have electrons being pushed in from this side. So that means it's less stable. So these rules here, you can either form 1-bromobutane, okay, or you can form 2-bromobutane. Your 2-bromobutane, which is this here, this being produced, is more likely to be formed because the intermediate is more stable. This is a secondary intermediate. Okay, whereas if it was 1-bromobutane, that could be formed, but it's a minor product. The reason why it's a minor product is because the intermediate would be a primary carbocation which is not as stable. Okay, so it's all about the mechanism here, but I'll put the answer up on the screen so you can, so you can see it. So let me just drag this down. Okay. So the answers is 2 marks for this. So the first one and the second one. So the secondary carbocation, okay, or the carbocation with the most attached alkyl groups, that's your first mark. So that's the one, that's why the major product is named like that. And is the most stable intermediate, so is the most likely to form. Remember your secondary carbocations in order. Primary is the least stable, secondary, and then tertiary. So if you can form a secondary or tertiary, then that's going to form your major product. So your hydrogen is going to add to the side where a secondary carbocation can be formed. Okay. So this you can also reference Markovnikov's rule, which is at the bottom there. So if you study OCR Edexcel, then you need to know that term as well. AQA you don't, but you can write it down if you want. It doesn't. You're not going to lose marks. So that's the official one. Okay. Right. So that's it. I hope that was helpful. Please share and like the video if you did find it helpful. That would be fantastic. I do all these for nothing. So all I ask is you hit the subscribe button. That'll be absolutely fantastic. And also you may have seen I'm doing another video on spectroscopy. I'm mainly covering the year 1 side because I imagine most people watching this are probably likely to be year 1 going into year 2 with all the issues happening so far with coronavirus. So I'm mainly targeting that side because you probably may have covered that already. So the video on Thursday at 12:50, well 12:50 start, 1 PM start, will be on infrared and mass spectrometry. All the links are there in terms of the video. So there's the video link, the live lesson, and also the questions on there as well if you want to go through that. So we'll do that on Thursday. If you can join me, that'll be absolutely fantastic. Okay. Can you go quickly back to question 1 if possible? E1 part 3. Let me just check. It might be 1 part 3. Yeah, give the formula of another possible organic product reaction. Yep. So what I'll do, I'll quickly go back. I'll go back to that. Actually, that might be quite difficult. I'll tell you what, the person who said that, which is, I think it's Benin, if you go to Allery Tutors on my Twitter and just direct message me, and I can give you that answer there. Okay. Or what you can do actually, this is a live stream, but it will be published on Allery Chemistry. So go and have a look on there. The video's on there. It takes YouTube I think about 6-7 hours to actually get it sorted, but it will go on there eventually. So if you want to have a look at this again, obviously later, then you can. All right. Brilliant. All right, thanks very much everyone. I hope that worked smoother than last time. I think it's better using traditional whiteboard, I think. Yeah, so no, thanks very much for your time. Please subscribe. I can't say that enough times. That'll be absolutely fantastic. You probably already are subscribed anyway, but share the video, like it, use the hashtag so people can find it easier. All right. Brilliant. Okay, Benin's got that. Fantastic. Yeah. So just direct message me. That'll be easier. Right. That's it. Thanks very much for your time, and I hope you enjoy. It's nice and sunny up here in Morpeth, but I hope you enjoy the sun. All right. See you later. Bye bye.